Hello everyone, welcome to our video for today. This is the full discussion explanation of our previous project. This binary coded decimal counter. So from binary to decimal counter. Now we started with our truth table. So this is the truth table for 7 segment display up to 7. So only up to 7 since we're just using 3 variables x, y, z. So the counting is only up to 7. So if we proceed this to like 8, 9, 10, so on and so forth, then we have to have 4 inputs. So like W, X, Y, Z. So like 16 combinations so that we can reach up to 7, 8, 9, 10, 11, 12, 13, 14, up to 15. 0 to 15. That's 16 combinations of 4 inputs variables. So by this time we limit only to 3 variables. That's why we limit also our counting to 7. So because like if we make this as 4 variables like 16 combinations, so our diagram must be maybe times 2 of these combinations of logic gates, and our Boolean functions is also longer than these functions. Okay, so that's why again we limit it to 3 variables, just to show you guys how to make a circuit out of basic logic gates. Like for example this one that we decided to have this output from 0 to 7. So from this truth table that we made from our last video, so like at the count of 0, 0, 0, so our display must be, the output is 0, so must be A, B, C, D, E, and F. Okay, 0. So at the count of 0, 0, 1, the decimal equivalent is 1. So BC. So that's why I put here BC as 1, 1. Then here's the decimal equivalent. So number 2, 0, 1, 0. So it must be A, B, G, E, and D. 2. So the count of 2, so segment will goes to high, like 2, like A1, B1, D1, E1, and G1. Okay, so 2. Number 3, at the count of 0, 1, 1, then A is 1, B is 1, C is 1, D is 1, and G is 1. 3. 1, 3. A, B, G, C, D. Number 4, the count of 4, 1, 0, 0. So B is 1, C is 1, F is 1, G is 1. So 4. And number 5, 1, 0, 1. So A is 1, B is 1, C is 1, D is 1, F 1, G 1. So that's number 5. Okay. And number 6, 1, 1, 0. So A is 1, B is 1, D is 1, E 1, F 1, G 1. So 6. Okay. Then the last is 7, 1, 1, 1. So A1, B1, C1. And that's it. E1, B1, C1, 7. So A, B, C, 7. So 7. So that's the last counting. Now, this 1, 1, 1, 1 here, at the count of 0, this is the equivalent Boolean function. A, X bar, Y bar, all zeros here, like A is 0, so X 0, Y 0, then C 0. So okay, again. So this is for this combination 0, 0, 0. This one, if we get the function of that, sorry, not horizontal but vertical, sorry. It's vertical, A, like this. So 0, 0, 0, 0, 1 up to 1, 1, 1. So this is the equivalent Boolean function, X bar, Y bar, Z plus X bar, Y, Z bar plus X bar, Y, Z plus X, Y bar, Z plus X, Y, Z bar plus X, Y, Z. Number 2, for B, so this one for B, this one X bar, I will not read anymore, so that one. For C, this one down, so C, this one. For D, all this one. For D, for F, for E, for F, for G. Then every Boolean function here, A, B, C, D, E, F, G, we made a key map to reduce these functions, like for A. So key map for A. So since 8 combinations, so 8 quadrants. So X, Y at the top, then Z at the bottom. So these are the ones in letter A. This one. So the simplified function is this one, X bar Z bar plus XZ plus Y. So out of this long function here, the original function, that's 3, 6, 9, 12, 15, 18 variables. Then we reduce it to X bar Z bar plus XZ plus Y. So I discussed this already last video. This one, how to simplify here, like for example here, this pair 1, 1, 0, 0, 0, 1, then 0 in variable Z 0. So the remaining here is X bar and Z bar, X bar and Z bar. y bar y cancelled. So also this one, these two pair here, 1 1 1 0, then 1 for z, then cancelled y is cancelled, so the remaining is x and z, so xz. Then this 4, if the more quadrants are involved in like simplification, so the lesser the variables. Okay, like this one, 4 quadrants, so as one pair, the 4 quadrants, so the remaining here is only y, because z 0 1 cancelled, and also at the top, like x 0 and 1 cancelled, so that's why the remaining is only y. Okay, so that's the final function here, x bar y bar, x bar z bar plus xz plus y. So same with b, c, d, e, f and g. So same explanation, guys. So from b, for b, the remaining is x bar y z plus y bar z bar. For c, x plus z, z plus x bar y bar. And d, a little bit still longer in letter d, because we cannot simplify that much, no? So still, how many variables? 2, 4, 6, 8 variables. X at least reduce to 8 variables from the original. For d, 3, 6, 9, 12, 15. So we reduce to 8 rather. So finally, x bar z bar plus y z bar plus x bar y plus x y bar z. X y bar z, because this one here has no pair, so he's alone. So for the e, and this is the smallest variable, x bar z bar plus y z bar, then f x z bar plus x y bar plus y z bar, y bar z bar. And the last but not the least is x bar y plus x y bar plus y z bar. Okay, so this is the logic diagram, and this is the display, and this is the actual. Now, so, and also I made another circuit that duplicate this complicated one. So this one using only 3 ICs, and this is automatic. It counts automatically, like not same as this, as we do it manually, like 1, 2, 3, 4, 3, 4, 5, 6, and 7. Okay, but this one, the circuit is automatically count from 0 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So because only one digit, we just put one 7 segment display, and this is also can display only one display like this. So if we need 2 digits, then we need also 2 decoder. Now this for LED here, this indicates the output of our BCD counter, this one, the 393. So like it counts also from this is the equivalent of this LED here. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, then reset back to 0. So actually this for combination, it must be from 0 to 15, because this is for combinations. It's what same as this, no, from 0 to 16, but it counts only up to 9. Why? Because we add another IC like this one, the 7408 AND gate. So because this IC, this one, this BCD counter has a reset pin, that if you want to reset the counting to what number, then you can reset this IC. So like here, this is the drawing. This is the 393. This is the 74393. So this is the reset pin. This is the reset pin. Then we connect to this 7408. So this is AND gate. Okay, so the one that we use here, some AND gates here, like this one, these are AND gates. So these AND gates, every time, why it limits to 9 and back to 0? Because at the count of 10, here, there's this 4 outputs here, from 00 to 111, 15, from 0 to 15 in decimal, because we can only display one digit up to 9. So at the count of 10, this 10 in binary is 1010. So this one, these two ones here, which is connected to the 2 inputs AND gate. So this is like when this A and C will count as 1, so the one will enter to 2 inputs AND gate, 2 ones, so 1 1. So this will output also, that can provide an output of 1 as well. So that will trigger to back to the reset pin, because this pin, if not used, this must be connected to ground, so that your counter will count up to 15. But since we limit to up to 9, so we have to have a reset at the count of 10. Here, when the counter count 10, then it will go back to 0. Okay, it will go back to 0 and count again to 9, then back to 0, 9 to 0. So Look, if I will remove this reset, this one, this is actually the reset pin. This one, I will remove that one. Okay, what will happen? So, something wrong with the counting, no? But if we connect that one, if we connect this to ground, this one, this is the reset pin. Connect this to ground. This is the blue line here. Okay, so this will continue to count 4, 5, 6, 7, 8, 9, that's 10, 11, 12, 13, 14, 15, then back to 0. But those numbers 10, 11, 12, 13, 14, 15, those are garbage. So you cannot read that anymore because that's 11, 10, 11, 12, 13, 14, then 0. Okay? So that's why we connect that to AND gate to trigger the reset pin of the BCD counter, this one, this IC. So we will connect again the okay. So 9, then 0. So that's how to reset this counter, BCD counter 393. So that's all for now, guys. And this one I will dismantle this one because we'll use this breadboard for another project. Okay, so I will show you how many ICs we use in this project. How many wires we use? See how many ICs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 ICs. But this one is only 1, 2, 3. Actually, this 10 ICs here is the corresponding one IC is only this one. This 7447. because this one is a counter that represents our manual counting here, this one, and this is the clock. This is automatic, provide a signal or a clock signal to this counter. Then counter will decode that to 7 segment display to binary. No, to decimal rather. This is a binary and this is the decimal display decoder. Okay, so this 04 at NOT gate, 08 AND gate, 08 AND gate, 32 OR gate, 08 AND gate, 32 OR gate, 32 OR gate, 08 AND gate, and this one actually this is the CMOS IC. So these are the TTL IC and this is the CMOS. We'll discuss maybe that later. What is the difference between TTL and CMOS IC? So this one is CMOS. We combine these two TTL, but it works fine. Okay, this is also a CMOS. This is also a CMOS, and this is TTL. This is TTL. And this one is a multi-purpose IC, no? Very popular IC we use in digital circuits. So again, this ICs here, 10 ICs. That's only this is only the equivalent IC for these 10 ICs here. So that's how simple, if this, because of the technology, this IC is combined in one just chip like this. So but the purpose of doing this project is just to tell you that all advanced chips or ICs were based on this basic ICs or gates. So like this one composed maybe of how many gates inside, we don't know, no? So but based on our project, or let's say experiment, is we can tell that these ICs are only inside of this one IC because it shows you have same display. Okay, right? So I think that's all for now, guys. Until next for our next project. So you see, look at how many wires we use just to display one digit. Okay, and this only how many wires here, same as the result is same as this wires we use. Okay, that's all for now, guys. Thank you so much. Bye.